Remarks on the backpropagation algorithm. In this topic, we will study convergence and local minima, representational power of feed-forward networks, hypothesis space search and inductive bias, hidden layer representations, and generalization, overfitting, and stopping criteria. We will first see what is local minima and global minima. Machine learning is at its core an optimization problem. We are looking to find an optimal model for our data, usually using gradient descent. Imagine plotting the results of our cost function for every possible model that exists for our data set. Some are better than others, so we end up with a landscape of peaks and troughs. If the problem space we are searching has what is known as a convex shape, it is shaped like a bowl with ridges around the outside and one big trough. When that is the case, we can find the globally minimal model by simply making incremental improvements to our model. Every improvement takes us a step closer to the bottom of the trough. Eventually, we won't be able to improve it anymore. We have found global optimum. If the problem space is not a convex, it can be made up of a multitude of peaks and troughs, some taller or deeper than others. So, following the same strategy will only find us a local optimal solution. There might be a better one in another trough, but our search is stuck at a local optimum. Local extrema, which is also known as either local minimum or local maximum, are regions in a solution space where the solution is optimum in its immediate vicinity. Global extrema are regions in the solution space where the solution is optimum globally. Consider the diagram. The local minimum represents a minimum within a small area of the parameter space, whereas the absolute minimum of the whole parameter space is the global minimum. The point at which a function takes the minimum value is called global minima. However, when the goal is to minimize the function and solved using optimization algorithms such as gradient descent, it may so happen that function may appear to have minimum value at different points. Those several points which appear to be minima but is not the point where the function actually takes the minimum value is called local minima. A function can have multiple minima and maxima. The point where the function takes the minimum value is called as global minima. Other points will be called as local minima. Similarly, the point where the function takes the maximum value is called global maxima. Other points will be called as local maxima. Local minima and global minima becomes important for machine learning loss or cost function. The backpropagation algorithm implements a gradient descent search through the space of possible network weights, iteratively reducing the error E between the training example target values and the network outputs. Because the error surface for multi-layer networks may contain many different local minima, gradient descent can become trapped in any of these. As a result, backpropagation over multi-layer networks is only guaranteed to converge toward some local minimum in capital E and not necessarily to the global minimum error. Despite the lack of assured convergence to the global minimum error, backpropagation is highly effective function approximation method in practice. In many practical applications, the problem of local minima has not been found to be as severe as one might fear. To develop some intuition here, consider that networks with large number of weights correspond to error surfaces in very high dimensional spaces, that is, one dimension per weight. When gradient descent falls into a local minimum with respect to one of these weights, it will not necessarily be in a local minimum with respect to the other weights. In fact, the more weights in the network, the more dimension that might provide escape routes for gradient descent to fall away from the local minimum with respect to this single weight. A second perspective on local minima can be gained by considering the manner in which network weights evolve as the number of training iterations increases. Notice that if network weights are initialized to values near zero, then during early gradient descent steps, the network will present a very smooth function that is approximately linear in its inputs. This is because the sigmoid threshold function itself is approximately linear when the weights are close to zero. Only after the weights have had time to grow will they reach a point where they can represent highly nonlinear network functions. One might expect more local minima to exist in the region of the weight space that represents these more complex functions. One hopes that by the time the weights reach this point, they have already moved close enough to the global minimum that even local minima in this region are acceptable. Despite these comments, gradient descent over the complex error surfaces represented by artificial neural networks is still poorly understood, and no methods are known to predict with certainty when local minima will cause difficulties. Common heuristic to attempt to alleviate the problem of local minima are: add a momentum term to the weight update rule. Momentum can sometimes carry the gradient descent procedure through narrow local minima, though in principle it can also carry it through narrow global minima into other local minima. Use stochastic gradient descent rather than true gradient descent. The stochastic approximation to gradient descent effectively descends a different error surface for each training example, relying on the average of these to approximate the gradient with respect to the full training set. These different error surfaces typically will have different local minima, making it less likely that the process will get stuck in any one of them. Train multiple networks using the same data, but initializing each network with different random weights. If the different training efforts lead to different local minima, then the network with the best performance over a separate validation data can be selected. Alternatively, all networks can be retained and treated as a committee of networks whose output is the average of individual network outputs. Convergence and local minima. The backpropagation multilayer networks is only guaranteed to converge towards some local minimum in the error space E, and it is not necessarily to be the global minimum error. We know that we have an error space. In this one, we are in search of local minimum, but the backpropagation multilayer networks, it won't guarantees that we will always get the local minimum in the error space. Still, backpropagation is a highly effective function approximation method in practice. Common solutions to attempt to address the problem of local minima include the following. Add a momentum term to the weight update rule. We are actually updating the weight, which will minimize the total error. Momentum term is the weight change of the previous step times a momentum parameter alpha. Every time we will change the weight which is considered earlier, and we will calculate the total error and find out whether the error is decreasing or increasing. If the error is decreasing, then still we will decrease the weight which is considered earlier. This step will keep on going till we will get minimum error. Second point is use stochastic gradient descent rather than true gradient descent. Gradient descent can be slow to run on very large data sets because one iteration of the gradient descent algorithm requires a prediction for each instance in the training data set. It can take a long time when we have many millions of instances. In situations when we have large amounts of data, we can use a variation of gradient descent called stochastic gradient descent. In stochastic gradient descent, the gradient descent procedure is run, but the update to the coefficients is performed for each training instance rather than at the end of the batch of instances. The first step is the order of the training data set is randomized. This is done to mix up the order that updates are made to be coefficients. In case of stochastic gradient, the cost is not summed over all the training patterns, but instead calculated for one training pattern. The learning can be much faster with stochastic gradient descent for very large training data sets and often need a small number of passes through the data set to reach a good set of coefficients. Altogether, the summary is optimization is a big part of machine learning. Gradient descent is a simple optimization procedure that we can use with many machine learning algorithms. Stochastic gradient descent refers to calculating the derivative from each training data instance and calculating the update immediately. Third point is train multiple networks using the same data but initializing each network with different random weights. As you know, the weights are initially picked up randomly with a small quantity. This weight is again updated to get minimum error. We are aware of neural networks and their countless achievements in multiple domains, from data science to computer vision. It is known that they are good at solving complex tasks that involve generalizations. Mathematically speaking, they are very good at approximating behavior of any complex function. Representation power is related to ability of a neural network to assign proper labels to a particular instance and create well-defined, accurate decision boundaries for that class. Now, question arises as what set of functions can be represented by feed-forward networks? There are three quite general results which are known about which function classes can be described by which type of networks. They are Boolean functions, continuous functions, and arbitrary functions. In Boolean functions, every Boolean function can be represented exactly by some network with two layers of units. Although the number of hidden units required grows exponentially in the worst case with the number of network inputs. To see how this can be done, consider the following general scheme for representing an arbitrary Boolean function. For each possible input vector, create a distinct hidden unit and set its weights so that it activates if and only if this specific vector is input to the network. This produces a hidden layer that will always have exactly one unit active. Now, implement the output unit as an OR gate that activates just for the desired input patterns. Continuous functions. Every bounded continuous function can be approximated with arbitrarily small error by a network with two layers of units. The theorem in this case applies to networks that use sigmoid units at the hidden layer and linear units at the output layer. The number of hidden units required depends on the function to be approximated. Arbitrary functions. Any function can be approximated to arbitrary accuracy by a network with three layers of unit. Again, the output layer uses linear units. The two hidden layers use sigmoid units, and the number of units required at each layer is known in general. The proof of this involves showing that Any function can be approximated by a linear combination of many localized functions that have value 0 everywhere except for some small region, and then showing that two layers of sigmoid units are sufficient to produce good local approximations. These results show that limited depth of feed-forward networks provide a very expressive hypothesis space for backpropagation. However, it is important to keep in mind that the network weight vector reliable by gradient descent from the initial weight values may not include all possible weight vectors.